Good evening, sir. My name is Karenji Maria Duffin, and I'm going to take you through our project. So, it's a credit card fraud detection system using quantum machine learning. So, the keywords here are quantum machine learning, quantum computing, as I said in the other videos. Then there are qubits, there is fraud detection, there is anomaly detection, as well as quantum algorithms. So, this project is about building a model that can detect fraud for credit cards. They'll actually save us from theft or being scammed. But we use quantum machine learning, is a which is a mixture of machine learning and quantum computing. So we shall have the different contents, which include the introduction, related work, problem statement, which focuses on the problem, then the research questions and objectives, the research contributions, the methodology, the the results, the conclusion, the references, and so on. So the first is the intro and the background. So this tells us what the project is about, where it comes from. So as I said, financial fraud, which is a global issue causing billions in losses annually. And then we have classical machine learning, which struggles with high data and real-time processing, then quantum computing. So basically, it's all about integrating classical machine learning into quantum computing to produce a model that can detect fraud. And so it combines both quantum computing and machine learning, as I said earlier. So why do we use quantum machine learning for fraud detection? It handles large datasets efficiently, and it detects subtle patterns in transaction data. Then the related works or recent trends. Now this is all about the research that's being carried out recently to actually improve or tell us more about quantum machine learning, how to make it better, the different styles they are using, different algorithms that they are using. So it's all recent trends. So we have variational quantum algorithms that are used for optimization and classification tasks. Then we have, under that, we have quantum neural networks, as well as support vector machines and quantum kernel methods. These are all machine learning algorithms. So they are the variation. So earlier, as I said, we have quantum annealing, which solves combinatorial optimization problems. The examples we have detecting fraud patterns in large data sets. We have quantum reinforcement learning. We have the hybrid quantum classical models. And for the recent trends, we have noisy intermediate scale quantum devices. So there are the current quantum hardware with limitations, for example, noise and decoherence. We have cloud-based quantum computing. For example, that's basically deploying a model to the cloud. You can use Google, Microsoft, AWS, Azure. There are many of them. Then the problem statement, we have the domain problem as well as the computational problem. So for the domain problem, we have credit card fraud, which is a widespread issue causing billions in financial losses annually. Then current systems rely on classical machine methods, which struggle with false positives, real-time processing, and scalability. Then for the other side, we have the real-time constraints, whereby fraud detection systems must process data in real time to prevent losses. Then we have the limitations in hardware. Also developing efficient systems is hard because quantum machine learning is quite expensive. Then we have the high dimensional data, whereby this particularly means having large data sets that are complex to analyze and are expensive. So I'm actually going to take you through the remaining slides. Thank you very much.
Good afternoon, sir. My name is Mr. Emerson, and I'm going to begin from where my colleague has stopped. That's so I'm beginning from the research contributions. So I have the specific contributions, like we developed a quantum machine learning model purposely for theoretical fraud detection, differentiating quantum algorithm like the quantity support vector machine algorithm, and then the quantum neural networks algorithms. So we also went ahead and built the first hybrid quantum classical framework. Its purpose, like for it, it combines the quantum and then the classical techniques for scalable fraud detections, like in the banks. Like we need, like there's sometimes fraud can be high, then unfraud down, and like they keep on changing ups and downs. That's why we use the scalable fraud detection. Also developed a novel quantum enhanced anomaly detection system that improves accuracy and then reduces false positives in real-time transaction monitoring. Also evaluated the computational efficiency of the quantum machine learning models as compared to classical models. Like this demonstrating significant improvements in processing dimension data. So also went to some architecture by beginning with the critical data set. After loading it, you select the data. After selecting, you go to the next step of like data set processing. Whereby you train, this is where we train the models over the data. And then we go to feature extraction. Then we use the classical machine learning, that's the neural networks, quantum hybrids. Well, then after that, we detected the fraud. So went to the dataset descriptions, whereby with this dataset one was good from Hindface, and it has 28 anomalized features and zero indicates fraud, non-fraud, rather one fraud. So we use the PCA for reducing the dimensionality, the dimensions of this data because it was so large. So another second data was got from data wall, and for it, it had the 30 features, including the ID, and then if you want to 28. So also had the EDA visualization, so the space didn't accommodate as you expected. We only put like two. The first one is for it is the class distribution background that highlights the class imbalances. Like as you can see, the non-fraud the green with the longest bar of 99.70%, then the 0.3% fraud including that is very imbalanced. So we also went to the like if you can like the scatter plot that shows the relationship between the two key features and how they separate fraud from non-fraud. So went to the output of our of our models, this is the first graph shows the learning rate versus the model performance, whereby you had the accuracy as 20 at almost 100%. So we had the precision was between 60 and then the 75 around there. Then you also had the recall was between 8 and 90. And then we had F1 score, which was between 60 and 80. And then the confusion matrix and the other graph. So because of time, I will like invite my next colleague to continue from where I stopped. Thank you, sir. These are some of the, thank you, sir.
Good evening. My name is Apio Dayan, and I'm going to be continuing where my colleague stopped. And this is slide 11. These are the module evaluation results that we got. This slide 11 and slide 12. And this we use these results to pick out the best model, which was the quantum QNN neural networks used it with extreme gradient boosting because though it has an accuracy of 0.8998, the model strikes a balance between learning and generalization, and it avoids overfitting while still being highly effective at identifying fraud. Then slide 13 is displays for graphs, which are the receiver operating characteristic graphs, and as well as two precision recall graphs that are used to evaluate the performance of a model, likely in a of a model, probably like a classification task. The graphs are split into original data and the smart data, which is synthetic minority over sampling technique to address class imbalances. The biggest limitation we had was lacking quantum hardware. We were using, of course, classical hardware, which we had available, and our models were taking up, our models could not train using all the features. So that was our biggest limitation. When we had, for our outcomes, the most prominent outcome was having a model that we could actually deploy, which was the quantum neural networks and with extreme gradient boosting. With our feature directions, for now, the feature directions that we're focusing on is real-world deployment, so that our model can be used to actually detect fraud in financial institutions and to detect it accurately and efficiently. Lastly, our acknowledgement. We express sincere gratitude to our supervisor, Dr. Marvin, for his mentorship throughout this research. Thank you.